Welcome. So we're going to just kind of finish up, talk a little bit about organic chemistry. To say we did. So we're going to get into a little bit of organic and some alkanes and stuff like that, which is organic chemistry. So let's get into it. So basically that first sentence there is pretty much the sentence you see in most organic books. Organic chemistry really is the study of carbon and carbon-based elements. When we talk about organic chemistry, it's all about really this sort of connection, carbons connected to carbons, and usually connected to those carbons are hydrogens all the way around there. We do see organic sort of compounds in every aspect of life, products like clothes, medicine, and so forth. The basis of organic molecules are really these two bonds, which again is our carbon-carbon bond, which is a nonpolar bond, as they both share the same electronegativity value, right? So something like 2.5 and 2.5. The difference in electronegativity value gives you obviously a difference of 0, which is a pure covalent bond. And also the carbon-hydrogen bond, where the electronegativity value is like 2.5 for carbon, like a 2.1 for hydrogen. So when you take the difference in electronegativity value, you end up with 2.5 minus 2.1, 0.4. As you might remember, maybe when you talked about bonding, 0.4 is sort of your limit for nonpolar bonds when we're sharing electrons. So if you do the difference in electronegativity, anywhere from 0 to 0.4 difference is considered nonpolar. A difference of 0, like we have on the top there, is considered basically sometimes a pure covalent bond, which means perfect equal sharing of electrons. Anything above 0.4, which I guess would be 0.5, to below 2 in terms of electronegativity, is usually some type of polar bond where we have unequal sharing of electrons. And not in all cases, but in most cases above 2, you do have an ionic bond. You don't really need electronegativity values to determine ionic bond. It should always be a metal and a non-metal, but that's sort of the cutoff here. So a vast majority of our organic compounds there are going to be non-polar, or at least parts of it is definitely going to be non-polar when we go through them. Now, because of that non-polarness of a lot of organic molecules, things like butane, which is an organic molecule, which is 4 carbons in a row, and some hydrogens there. This guy is non-polar, and that also means that it will be using dispersion forces as its main sort of intermolecular force. If you remember, dispersion forces are very weak intermolecular forces, the forces that hold one molecule together with the next. They are sort of temporary dipoles, induced dipoles, and these are things that typically have very low melting points and boiling points because it is a very weak attraction. That's also why a lot of the very beginning organic guys like methane, propane, butane, they're also very much gases in our normal conditions because of that weak interaction that occurs. Also, why a lot of organic molecules are said to be very volatile. They go into the gas phase very easily, which is why when you take organic, they stick you in a fume hood so you don't inhale everything that goes into the gas phase really, really easily. And that is very different than what we see with sodium chloride. Sodium chloride is obviously ionic, as we have no sharing of electrons here, but we have a transfer of electrons with our electrostatic attraction. And obviously, that is a very strong intramolecular force. If you remember, intramolecular forces are much, much stronger than any intermolecular force. And you might have experience of this at some point during your laboratory career. You usually at some point take some salt water and you heat up the salt water. The water will evaporate off. You'll be left with just the salt left over, like in your evaporating dish. You can heat the heck out of that salt. It will never really go into the gas phase under normal conditions. It will just start to sort of melt before it kind of will do that. because of that really, really strong intramolecular force. All organic compounds basically contain carbon, and the key with carbon, and especially in organic chemistry, is the idea that carbon will pretty much keep going until it reaches 4 bonds. So carbon always wants 4 bonds. Much like normal sort of Lewis structures, carbon never usually finds itself with non-bonding electrons usually. There are a few examples of non-bonding electrons on carbon, but pretty much, and definitely in an organic situation, pretty much most of the time you will have bonds that going into carbon. It should never have more than 4 bonds, as it has the 4 valence electrons. Although people, when they do start drawing organic things, like to just keep throwing on bonds to carbon and keep drawing lines. I've seen people draw like 12 lines to carbon. That's a lot of electrons. By the way, hydrogen still obeys the duet rule, which, like normal, means it just needs obviously 2 electrons. It should always look like that to get itself to helium, which is the noble gas that comes after hydrogen when we do that. Down here is methane. Again, in an alkane situation like this, we do have obviously our 4 electron pairs and our 4 bonds. So it takes on the tetrahedral arrangement here when we have something like methane or a single bonded carbon that happens. Now, carbon itself and a lot of organic compounds can form multiple types of bonds with other carbons. It can make single bonds, it can make double bonds, it can make triple bonds with other sort of carbons that are present. And actually on the bottom, we have an example of each of those. And in organic chemistry, there is basically what is known as the functional group. And the functional group is really the part of the organic molecule that makes it a certain type of organic compound. There's different types of organic compounds, and the part of the molecule that is known as the functional group basically identifies it as a certain type. It also, depending on the functional group, will give it different types of properties. So for example, if we look down here, the functional group for this first one, which is known as an alkane, is really the carbon-carbon single bond. So they're all single bonded. Those are a type of molecules known as alkanes. When we get a double bond, those are guys that are known as alkenes, E-N-E, functional group being the carbon-carbon double bond. And those guys that have a triple bond, those are known as alkynes here. And that is a carbon-carbon triple bond. Couple other things that you see is every time we put on another bond to carbon, we need to sacrifice a hydrogen at each carbon. Otherwise, you will end up with too many bonds. So when we slap on that second bond there, we lose 2 hydrogens. When we put on the third bond, we also lose another 2 hydrogens. That once again, as I mentioned on the previous slide for our alkanes, by the way, this is what's known as ethane, ends in A-N-E. That's sort of the common name. This is also known as ethene, E-N-E. And this last guy here is known as ethyne, Y-N-E. What I'm crossing out is the common names, and something, if you take it organic or will take organic, one thing that you'll learn is there's like 3 names for the same thing. There's like the formal name, there's like the common name, and there's like a historical name that people call it along the way. So you'll sometimes run into multiple names that represent basically the same thing. When we look at, again, our carbon here, once again, we have our 4 electron pairs and our 4 bonds, and that's going to give us our tetrahedral arrangement, and that is our 109.5 degrees Celsius. That is also sp3 hybridized carbon there. Again, you do hybridization. A simple way is to just count how many electron pairs you got going on there. So in case you have never done it this way, this is a good way to do it. You would count the electron pairs around whatever atom you're looking at, just like you would do geometry. So if you had a double bond or triple bond to count, it's just 1 electron pair. So this guy's got 4. That would be 1, 2, 3, and 4. That's an S and 3 Ps. So that's an sp3 hybridization. When we lay up that double bond in there, it does change what's happening there. That now has 3 electron pairs. As a double bond counts as only 1, and also has 3 bonds. That is our trigonal planar geometry. And that's got a bond angle. By the way, that is also the electron pair geometry. It's got a bond angle of 120 in that case. It has 3 electron pairs, which again, if you count it off, would be 1, 2, and 3 only. And that would be sp2 hybridized in terms of the carbon that's happening there. And lastly, here with our triple bond, say this carbon right here, it has 2 electron pairs. It also has 2 bonds. Once again, we count the triple bond as a single electron pair and a single bond, and that is our linear geometry. Also means there's only 2, so that's 1 and 2. That's an S and a P. So the hybridization here would be sp hybridized. It's got a bond angle of 180 there in terms of what's going on there. So not only does the double bond or triple bond obviously change the geometry that's happening here, change the bond angle, it also changes the hybridization of those carbons that are in the middle. Any questions on any of that there? So methane and ethylene here with this ethene, again, using plastics. Obviously, that's what comes out when we light our Bunsen burner as well. Some compounds are straight chains in organic chemistry, and some are sort of cyclic or ring type structures. So a straight chain like what we have here is pretty much what it means. It's pretty much all the carbons just run straight across. Over here is more what is referred to as a cyclic structure. It basically makes a ring type structure where you kind of take 2 carbons, 1 on each side here, and kind of close it up on itself. And it will make this really triangle type shape that will occur here. And that is what is a cyclic structure. And we add cyclo to the beginning part of the name because of that. And ANE, which means it's an alkane, and it has all single bonds. What I drew here is obviously what's sometimes referred to as line structure. In line structure, we pretty much just lay up lines and don't write anything else there unless it's necessary. Wherever there's sort of points or things come together are carbons. So that's 1 carbon, 2 carbons, 3 carbons. And since carbon needs 4 bonds, each one has 2 lines coming in, which means technically speaking, there are 2 hydrogens at each of those carbons. Obviously, in line structure, you typically don't draw the hydrogens in, or you don't write the carbons in. We could do line structure for the guy on the left here, which is propane, and it would look something like that, where this would be 1 carbon, 2 carbons, and 3 carbons. You don't usually put the circles, by the way, anyways, but those are, again, the carbons. And once again, at each of them here, they would have the appropriate number of hydrogens to get it to 4. That would be 3. This guy would be 2. And this guy here would be 3 as well. So that is line structure, which again, pretty much just lines. This, by the way, is what is referred to as the expanded structural formula. And it's basically where you draw out all the bonds to the hydrogens. A third type of formula, which is very commonly used in organic chemistry, is what is known as the condensed formula. And in the condensed formula, you basically just don't draw out the hydrogens. So if we look at this propane here, that is a carbon with 3 hydrogens, so you would write CH3. Next to it is a carbon with 2 hydrogens, so you would write CH2. And next to it is a carbon with 3 hydrogens, you would write CH3. So that is what is sometimes referred to as the condensed formula, where you do not draw out the hydrogens. Any questions on that there? Now, organic compounds typically will contain hydrogen, but as I mentioned before, What gives us really different sort of classes of organic compounds is along the way we kind of substitute out the hydrogens for other elements. Most common in organic chemistry is we see oxygen being inserted there a lot, nitrogen as well, and the halogens like fluorine, chlorine, bromine, and iodine do find their way into organic compounds very, very often. And, you know, as we sort of change the organic molecule, if you will, to incorporate some of these other elements like oxygen, nitrogen, and so forth, it does have the ability to sort of change some of the characteristics of that particular organic compound, because we may be introducing a more electronegative atom, which may create sort of a polar side to a particular organic compound along the way. These are some common sort of bonding patterns we see in organic chemistry. Hydrogen, again, always at the end. Our carbon, pretty much 4 bonds. Nitrogen typically will have the lone pair there. Oxygen, usually with like an OH there type of situation, and our halogens there. Oxygen as well will also find itself very often in organic chemistry in this arrangement, double bonded to a carbon. And as we'll see in a second, this is what is known as the carbonyl group. And this is also a polar group where the oxygen is more negative and the carbon is more positive. Carbon and oxygen being in the same row on the periodic table, where oxygen is further to the right, meaning it is more electronegative and it should create a polar bond. And that's important for a lot of reactions that involve guys that have that carbon-oxygen double bond that happens there. Here's a couple of oxygens here, and here we have what is known as methanol. And this group right here, this OH group, is the functional group for an alcohol. Is that OH group. That OH group is a polar group. So by actually putting that OH group on there, and by the way, that's why it's called methanol, OL, because this is an alcohol, OL. By putting that polar group on there, it actually gives something like methanol some solubility in things like water, because this OH group is a polar group, which is negative and positive. And that works well with something like water, which is pretty much identical to that, negative and positive on the hydrogens. And it allows some hydrogen bonding to occur. Hydrogen bonding can occur between water and something like methanol, which makes it soluble in it because of that ability to do so. So a lot of alcohols, because they do have that OH group on there, you know, as opposed to an alkane that doesn't have the OH group, just has the hydrogens, it definitely is a lot more water soluble because it's able to interact through hydrogen bonding. But as the carbon part of it gets really large, the solubility does decrease. So what I'm talking about is if you had an OH and a lot of carbons coming this way, after about 5 or so carbons going that way, the solubility pretty much drops to nothing-ish. It becomes really less and less soluble. It's what is sometimes referred to as steric hindrance. Pretty much you have this big non-polar part of the molecule that gets in the way of water being able to get to that OH group that is there, and it decreases the solubility a lot. So that's what you see a lot in organic molecules is, you know, there's sort of a side of the molecule that is non-polar. And then there is a lot of times these sort of groups that are polar. So, you know, it gives it a way to sort of interact in certain cases. On the right here is another sort of organic chemistry group here. Could go either way on this, so I'll just highlight that one. That is the functional group for this particular organic molecule. And that is basically the carbon-oxygen double bond with the hydrogen. That is what is known as an aldehyde. And that is the functional group for an aldehyde. That is like a common name we probably have heard of, formaldehyde, right? And formaldehyde is also known as methanol, AL. Now, both of these things are really based off of this guy, which is a 1-carbon alkane, which is methane. So methane, if you get rid of a hydrogen and put an OH group, becomes methanol, which is an alcohol. If you get rid of a hydrogen or a couple hydrogens and put the carbon-oxygen double bond in the H, it becomes methanol, which is an aldehyde. And they have some different properties. So again, methane, no hydrogen bonding happening there with water because it does not have the ability to do so. Remember, in order for something to hydrogen bond, it needs to be a hydrogen that is directly attached to a nitrogen, oxygen, or fluorine. So it makes a really electronegative difference there. So even though it has hydrogens, it cannot hydrogen bond in those cases, but the OH definitely can, and it increases its solubility, for example. As I mentioned earlier, you know, some different structure or type formulas. We have our condensed formula, which is this guy right here, basically. Most people will still draw the dashes in between. And it's important to remember that when you do have something like this, the connection, although it does appear that maybe it's the hydrogen in the middle of everything, again, the connection is what we see over here. It is the carbon to carbon connection, which is sort of the backbone of the molecule with the hydrogens attached on the outside. Once again, the hydrogens cannot be in the middle, otherwise they will end up with too many bonds. And again, we could do our line structure, which looks something like that. For this guy right here, which is butane, that would again be 1 carbon, 2 carbons, 3 carbons, and 4 carbons that would happen there. Again, each of them would have the appropriate number of hydrogens. Now, sometimes we do in condensed formula show a line to show a group attached, and that's a very common way that people will do that. Rather than just kind of going CH3, CH3, CH, CH2, CH3. The problem with doing it this way, if you don't do it sort of correctly, it implies that that CH3 is in the middle of those two, and that would give that carbon too many bonds. So most of the time people will draw that sort of group out, which is not part of the main part of the chain there, to indicate that it is not part of that run together. Or they will do something like this, use some parentheses. So sometimes you will see sort of a shorthand. If you have like that, that basically just means we have 4 of the CH2 units in a row. So that's a very common sort of shorthand, especially when you're dealing with really long stuff. Again, if you have sort of that situation like we were just looking at, this would be the proper way to do it. Put parentheses and the 2 on the bottom. But I would say 9 times out of 10, most people would probably draw it like we see there on the left, indicating that 1 single bond. The skeletal structure, which is really the line structure, as I talked about, really will have a junction, and it is typically drawn in this zigzag shape, and that is because alkanes are tetrahedral in arrangement, so 109.5. So as they each go tetrahedral, it gives that commonly referred to as a zigzag sort of shape up and down. I don't know how many I drew here, but if I count them, this would be 1, 2, 3, 4, 5, 6, 7, 8, and 9 carbons in this particular case. Now, if something is meant to be there, they will put it there at the end of the line. So if they want like a bromine there, they will write the bromine. If you see a line with nothing there, that also means that at the end there is a carbon, and that should have 3 hydrogens at the end. So sometimes people see line structure and they go, I just got like a line with nothing at the end of it. That again would be a carbon, and then it would need 3 hydrogens to make sure it has 4 bonds. So usually in line structure, if you just see a lonely line by itself, it should be what's referred to as a methyl group, carbon at the end. If they want something there, they definitely will draw it in at the end of the line, and you would see it. By the way, in line structure, you also can do a little double bond action, just draw another line. You could do a triple bond action, draw 3 lines. Even though technically this is not correct in geometry, as that triple bond there would straighten it out linear, but you know, you could draw it that way. That technically would look like that. Triple bond and double bond. Line structures are used a lot for cyclic compounds. This is cyclohexane, and again, this is typically what most people would draw for cyclohexane. And once again, at each of these points here is a carbon, and that would obviously be 6 carbons. And in this case, each carbon has 2 lines coming in, which would give us our 2 hydrogens that we see to the left here on each of the carbons all the way around. That again would be the expanded structural formula. That would be our line structure. And if you needed to do a condensed, it would look something like this. And it looks something like that. Any questions on any of that there? Now, sometimes we do put other groups on it, having this group here, which once again is our alcohol functional group, and is a 5-member ring, which is where the pentane part comes from, OL for the alcohol, and we do put cyclo at the end. In this particular case, this carbon right here would definitely be carbon number 1, where the functional group is located. So typically the functional groups in most organic molecules, you want to make sure that they end up with sort of the smallest number. In a ring structure, you basically, wherever that group ends up, would be carbon number 1. So when we talk about functional groups, a lot of times in organic chemistry, R is used not for functional groups, but to basically represent the carbon part of the molecule. And then we have it attached to our functional group. So if you have something like ROH, that is our alcohol. And then once again, the R would be 1 carbon, 2 carbons, however many carbons would be attached there. So let's take a look at some of these different functional groups. We talked about a few of these here at the beginning. Our alkanes, which again is our carbon-carbon single bond, which is our functional group. That's a double bond. Sorry, again, carbon-carbon single bond. And again, it has a general form of CnH2n plus 2. N is the number of carbons. So 1 carbon, 2 times 1 is 2, plus 2 is 4, gives us methane. 2 carbons, 2 times 2 would be 4, plus 2 would be 6. So 2 carbons should have 6 hydrogens as if it's an alkane. Now our alkene is our carbon-carbon double bond, which has a general form of CnH2 times N. We lose those 2 hydrogens when we make the double bond, so we take them away. And our alkyne is our carbon-carbon triple bond, which is CnH2n minus 2. We got to subtract off 2 more hydrogens to make that bond. Another class of organic compounds are what are referred to as being aromatic. Aromatic contains a benzene ring in it, and benzene is this guy, a 6-carbon guy that has 3 double bonds in it. You could draw a resonance structure where the double bonds move to the other side. And in some books, they simply will just lay up a circle in the middle to indicate that those double bonds are moving around and stuff like that. So those are all representativeness of C6H6, which is benzene. So anything that has a benzene ring on it is a class of organic compounds which are known as aromatic. So for example, you could throw a benzene ring with an OH on it, and this is what is known as phenol, which is basically the alcohol sort of version of a benzene ring there, and obviously has properties of alcohols as well. It is an aromatic, as it does have that on there. There's a lot of historical type names that go with benzene and things attached to it, like this guy here. This is what is sometimes referred to as methylbenzene or more toluene. Did I spell that right? Toluene. There we go. So that's a historical type name. If you have a benzene ring with an NH2 on it, that is known as aniline. So there's a lot of really historical sort of names that are used still a lot today that involve benzene rings and things that are attached to it. So let's take a look at some of these other functional groups. These guys we all talked about here a second ago. Once again, carbon-carbon single bond for alkanes, the functional group, double bond, triple bond, and obviously our aromatic that has the benzene ring involved. Some other functional groups, alkyl halides. Alkyl basically means carbon. Halide is a halogen. IDE is a negatively charged halogen. So that is like a chloride, a bromide, an iodide finds its way on there, and you get a alkyl halide. An alcohol is the functional group, as we talked about, that has the OH. Again, that is a polar sort of group, so it allows a lot of really low numbered carbon alcohols to be soluble in water. Ethers has a functional group of a carbon, oxygen, carbon run. Ethers put you to sleep in case you're tired, right? Amines have a nitrogen containing group. And these guys are what are sometimes referred to as ammonia derivatives. Ammonia, as we know, is a weak base. So a lot of amines basically do a lot of base type reactions, since they are basically derivatives there of ammonia. Thiols are the very smelly guys. They have sulfur, so they are sulfur containing groups. They're very similar to the OH group, except that it is sulfur. So sulfur is a little bit less electronegative than oxygen on the periodic table. Sulfur is underneath oxygen. So it's still polar, but again, not as much, obviously, as what we see with the oxygen. And it can't necessarily hydrogen bond like an OH1 can, because it's not that much electronegative. As I mentioned earlier, this is a very important group as well as a carbonyl group. This guy here is what is sometimes referred to as the carbonyl carbon. And it is, once again, a polar group, carbon and oxygen, carbon being more positive. Really important for a lot of reactions that occur there. A lot of reactions occur there. A lot of organic reactions and mechanisms are really based on the very simple principle of positive and negative. So if you have something that's negative, it will be attracted to the carbon because it's positive. So the opposites attract, sometimes referred to as a carbocation it will make, and it will come in and things will attack. And that's really how things get shifted around here. There's several functional groups that have that as part of it. So we saw one earlier, which is the aldehyde. It has the carbon-oxygen double bond with the hydrogen. This group will always be at the end of a molecule because it has the hydrogen at the end. So it can never find itself in the middle. Otherwise, hydrogen will have too many bonds. A ketone is basically a 3-carbon run where the second carbon has the double bonded oxygen to it. So you need at least 3 carbons in a row there to make a ketone. So really the simplest ketone you can have is actually one with 3 carbons. You can't have anything less than that because you don't have the 3 in a row to do so. By contrast, you will never ever find the carbon-oxygen double bond at the end of the molecule in the ketone because you need those 3 carbon runs. So it's got to at least be the second one in. It could be even more in, but it can never be at the very end, the carbon-oxygen double bond. Other ones, carboxylic acid is this functional group, carbon-oxygen double bond with the OH. We've seen this guy a lot. That's our good friend. Acetic acid is one of these guys. And typically speaking in formulas, when it is written like that, it is that guy right there that we are talking about. And acetic acid, right, which is here. Looks like this when you draw it correctly, I guess. And again, it has a carboxylic acid, and obviously it is a acid, and it is this hydrogen once again that is involved in basically the acid part of it. An ester is basically like a carboxylic acid, except it's missing the hydrogen, so it's got the carbon connection at the end rather than the hydrogen. And that is because you make an ester through a reaction that's known as an esterification reaction. You take a carboxylic acid, you take an alcohol, and you squish them together. You take water out and put them together. Esters are responsible for a lot of smells and flavors and smells that we know, like, you know, the smell of like bananas, peaches, you know, those type of things. There are a lot of very fragrant type of smells, pineapple type smell, or esters and stuff like that is responsible for those type of things. Another functional group is an amide, and that is also very much like a carboxylic acid, except that it's got the nitrogen group attached to it. And this is basically made by taking a carboxylic acid and an amine and sticking them together, taking out water. You might also recognize this bond. I believe they do a little peptide bond, like that guy right there is an amide bond. When you do some proteins, amino acids, and backboning of the amino acids together, you take out water, put them together, make that peptide bond that is there. So that's an amide bond made again by taking carboxylic acid basically and an amine. Now, as you can see, a lot of these different functional groups, that is the part of the molecule that makes it a certain type of organic compound. And that really is, in most cases, where sort of all the action takes place. So sometimes people think, you know, it's like crazy stuff happens with all the organic stuff. But really, it's just that small part of the molecule where the functional group is located, where, you know, when it goes through a reaction, that's pretty much where it all sort of takes place. Most of it happens in that sort of area. Any questions on that there? So let's talk a little bit more about alkanes. Alkanes, as we talked about, are guys that are carbon-carbon single bonds. We have what are referred to as saturated alkanes, or sometimes they're referred to as saturated hydrocarbons. And the name hydrocarbon is pretty much what it sounds like. It's carbons and hydrogens together. So if we have something like this guy right here, which is our butane, every single carbon that is present has the maximum number of hydrogens it should have. And that is what saturated means. It means it's basically got the exact proper amount of hydrogens to get carbon to 4, is not missing any. We mess that up when we start adding like a double bond. So if I laid up a double bond there towards the middle of this guy, we will lose a couple of hydrogens on those two center guys. Bad reflection, but I think I got it there. 1, 2, 3, 4. So we lost a couple of hydrogens from those carbons, which is necessary in order to make the double bond. And this situation is what is referred to as being unsaturated. So an unsaturated hydrocarbon is basically one where you got at least one double bond, maybe more, but you basically don't have the maximum number of hydrogens that should be present. Any questions on that there? Cycloalkanes, again, basically lose a couple of hydrogens. They have CnH2n because it has to close up that ring. Most cycloalkanes are usually drawn in line structure form, and they're like our geometrical shapes. Once again, there's like a triangle, there's a square. We have this guy here, which is our 5-member, and then obviously we have our 6-member ring. So this has got 3 carbons, 4 carbons, 5 carbons, and 6 carbons. And when we name these, because they're all single bonded there, they are alkanes. And we actually do put cyclo in front of it. So this guy has 3 carbons. This is what is known as cyclopropane. This guy has 4 carbons, which is known as cyclobutane. We'll talk about how we get to these names in just a second. These are cyclopentane for 5 carbons, and cyclohexane there for 6 carbons. So we put cyclo in the front. It has 2 less hydrogens because it did have to kind of close up on itself. And again, usually they will kind of use the line structure to represent these guys rather than condensed or any other type structure. So let's talk about really the first 10 alkanes, which is really important. Pretty much everything is based off of the first 10 alkanes, everything from all types of functional groups, different organic molecules. For the most part, just go back to these sort of first 10. We have one carbon. Again, these are all alkanes, which means they all are going to run CnH2n plus 2. Again, one carbon, 2 times 1 plus 2 is 4 hydrogens, 2 carbons, 2 times 2 is 4 plus 2 is 6 hydrogens as you go through there. This is the IUPAC way of naming, which you learn a lot about when you take organic. Not really. They just tell you to give the IUPAC name. Stands for the International Union of Pure and Applied Chemistry. They are the people you could thank for having to name things the way you do. Methane is 1, ethane is 2, propane is 3, butane is 4, pentane is 5. Let's add the other guys here. 6 carbons would be hexane, and it would be C6H14. 7 carbons would be heptane, ANE. 7 carbons, 16 hydrogens. 8 carbons would be octane. 9 carbons would be nonane. And lastly, 10 carbons would be decane, ANE. So everything, including group names, all other names, you know, they really do fall back to these guys' names. You know, and it goes from all sort of aspects of groups. So for example, if you had something like this, which is just all carbons and hydrogens, that's 3 carbons, that would be propane. You put a double bond in there. Gives me H2, gives me H, if we can get it in there, gives me H3. This would be propene. You do a triple bond in the middle there. This now becomes propyne. Doesn't matter if it's, you know, double bond, triple bond or not. You know, you have something like this. This is an alcohol, which also has 3 carbons, known as 2-propanol. Also, obviously, based off of the 3 carbons. You got this guy, which is our aldehyde, that has 3 carbons. This is known as propanal, Al. So the number of carbons all really relate back to this guy. By the way, this guy right here, 2-propanol, also known as Isopropyl Alcohol, also known as rubbing alcohol, as we were talking about earlier, that you know, these things have multiple names sometimes for the same thing. So those are 3 names for that same guy. So our methane, again, having our 1 carbon and our 109.5. Again, our ethane, given our zigzag shape starting to form here with our propane, as you can see there. Sometimes people draw organic molecules and just draw like the end up or the end down, and they figure, well, I just drew something different. And one thing that you do when you're in organic chemistry and trying to figure out names and things like that, it is all about the longest continuous carbon chain. So you always want to find the longest continuous carbon chain. So for example, the first guy here is basically 3 in a row, which is propane. Now, although this may look different to you, if you start here, 1, 2, and it's still 3 in a row with nothing else attached, they're both the exact same molecule. They're both propane, even though they may appear different, because they have the same longest number of carbons there and nothing else is attached. They're both propane. So sometimes people think they do draw something different by just kind of, I'll just bend it up, bend it down, and stuff like that. A really good way to know whether or not you really did draw something different is to name both things. And if you end up with 2 different names, then you definitely drew something that's different. If you end up with the same name, you just drew the same thing that looks different, provided you name it correctly. Now, this happens sometimes when we have what are referred to as isomers of things. And isomers are guys that have the same molecular formula as we talked about sort of with transition metals chemistry or complex ions, but have different arrangement. Here, if we take the longest continuous carbon chain here, that is 4 in a row. Nothing else is attached. and that would be butane. If we take the guy on the bottom there and kind of look and see what we got going on, I'm just gonna do it like this, I think. Actually, no, we'll do it this. We'll draw it out. So if we draw the guy on the bottom, we look something like this, I think. When we look at this, if we go with the longest continuous carbon chain, we could go straight across, which would be 3. We could also go straight and then up, which would be 3 as well. It doesn't really matter which way you go. If you have multiple options, personally, I like to go with the straightest option. Is sometimes the better way to do that. But you could take any option you want. It should come out the same. So when you go to name something, the first thing that you want to do really is find the longest continuous carbon chain. It will not necessarily always be the straightest one. You could go straight, come up, and come back down. The only thing you can't do is backtrack. So you got to start in one direction and go until you hit a dead end and count up how many carbons you have. When you do that, that will be the base of your name, which is 3 carbons from our alkane. They're all single bonded. The base of our name here will be propane because of that. We then see that not part of the main chain is this guy right here, which is what is referred to as a group. More specifically, it is a carbon-based group, which means it is sometimes referred to as an alkyl group. Alkyl for carbon. And those groups are also based off of the first 10 alkanes. That is a 1 carbon group. And 1 carbon with all the hydrogen is known as methane. We cannot attach methane the way it is with its 4 hydrogens because then it will have 5 bonds to carbon. So we actually have to get rid of one of the hydrogens to make room for it to be able to bond into the chain, and that's where it would bond. And it goes from methane to YL at the end. This is what is known as a methyl group, and it's been based off of it. If you had 2 carbons, it goes from ethane to an ethyl group, if it's a group, propyl group, butyl group, and so forth. And that's what that would be. So we would put that into our name as sort of the group that's not part of the main chain, and that would be methyl propane. But organic chemistry is really all about location, location, location. You need to tell people where everything is located. So what we typically do is number the main chain, which this would be carbon 1, this would be carbon 2, this would be carbon 3. The other option of numbering would be to start over here as carbon 1, carbon 2, and carbon 3. When we number the chain in an alkane, we want to make sure that the group ends up with the smallest number. Doesn't matter in this case which way we go. It really doesn't matter. That group's at carbon number 2, no matter which way you go. And that is where the 2 comes from. And this is what is known as 2-methyl propane. And that still has the same number of carbons as the guy on top, which is butane, and has the same number of hydrogens as the guy on top. They are isomers of each other. They are basically the same formula, right? But different connectivity. We actually have 2 different names, which tells us we have 2 different compounds that are present here in this particular case. Any questions on that there? Typically in organic chemistry, when we name, we do a little, between a number and a letter, we do a dash. And if you happen to end up with a bunch of stuff on your screen here, if you happen to end up with 2 numbers in a row, you separate them by a comma. So between a number and a letter, we do a dash, which is why there's a dash here. And if you happen to end up with 2 numbers in a row, you do a comma in between. Any questions on that? Yeah. Yeah, this would be the IUPAC way of naming it. You wouldn't necessarily call that probably, You could, I guess, because it does have the iso group there in the butane, but most of the time you would probably go with a 2-methylpropane because it's the IUPAC way of naming. There are certain things that are sometimes called that. There's an isobutyl group that looks like this where it's attached to something else, and that's, yeah. This is what is known as isobutane, and again, this is more of a sort of a common name way of doing it, and it's because technically this is like an isobutyl group that's there as well. So you'll sometimes see it like that. This is really the IUPAC name right there where you have the 2-methylpropane, which is usually the way you want to name most things. Okay. All right, so butane and isobutane or 2-methylpropane there are isomers of each other. And again, they are basically two things that have the same formula, but different connectivity. Constitutional isomers differ in the way the atoms are connected to one another. These again have 2 carbons on each of them. They have 6 hydrogens and 1 oxygen, but the different connectivity here, for example, that is going to be our alcohol, and this is going to be an ether, carbon, oxygen, carbon, which is an ether here. So again, they have very different functionalities as well. The OH group, again, will allow us to do some hydrogen bonding. No hydrogen bonding sort of happening here with our ether. So even though, again, they're comprised of the same thing, they will give you some different sort of results. Here, again, are a few different sort of isomers. We did the 2-methyl-butane here. We'll take a look at each of these names and just show you how we get to there. The first thing that you want to do sort of with the name is you always want to find the longest continuous carbon chain. So that is always the first thing that you want to do. So clearly in this thing, it's not too hard. It is just 5 carbons in a row, and that is basically going to be pentane. In the case of our second thing here, our longest continuous carbon chain would actually be straight across here. We have 1, 2, 3, 4. You could also go straight and then go up and get 4 as well. So you could kind of go this way as well and get 4. Once again, it doesn't matter which way you go. They all should give you kind of the same name at the end of it. Once you find the longest continuous carbon chain, that once again will be the base of your name. So that's 4 carbons. So the base of our name here would be butane. Now there's going to be something that is not part of the longest continuous carbon chain. And once again, this is going to be our group that's attached. And this once again is a 1 carbon group, which is based off of methane. And that would then become a methyl group, which is where our methyl comes into play here. So once you do that, you want the longest carbon chain. You want to ID the groups that are there. You then want to number the chain, the longest chain. And once again, you pretty much have really only 2 ways to do it, left to right or right to left. So if we go left to right, that's 1 carbon, 2 carbons, 3 carbons, 4 carbons. Right to left, 1 carbon, 2 carbons, 3 carbons, 4 carbons. We always want to number the longest carbon chain to give the group in an alkane the smallest number. So in this case, we would need to go left to right, as that would give the methyl group basically number 2. If we went the other way, our methyl group would be at number 3, and it is as simple as 2 is smaller than 3. And that would be where we would want to go, and that again is where the 2-methyl-butane comes from. Butane telling us there's 4 carbons in a row, and 2-methyl telling us at the second carbon there is a methyl group that's hanging out there. Question on that one there. Now, if we come to our last one here, the longest continuous carbon chain, 1, 2, 3, you could actually get it multiple ways. You could go up to get 3, you could go straight and go down to get 3. But once again, if you do have sort of a straight one, that's usually a good one to do. Sometimes it's helpful to put a box around it so you can kind of see it. And then you want to highlight your other groups that are there. That is a methyl group on both of those guys. So that is a methyl group, and that is a methyl group. And in this particular case, and it sometimes does happen that we do end up with multiples of the same group. doesn't have to be on the same carbon, but in the same compound. So in this case, we do use a prefix to help us out. So prefix for 2 is di. So again, 3 carbons in a row is propane. This is now going to become dimethyl, as there's 2 of them in there. And once again, we do need to get the location where those are found. And in this case, 1, 2, 3, or 1, 2, 3. It doesn't really matter which way we go in terms of the numbering here. But we do need to give the number twice in this case. So this is a 2, 2, as we separate the numbers by a comma, dash dimethyl for the 2 methyl groups in the compound, propane, like we see there. Any question on that name there? There's our other guys. There's our 6 we did before. The IUPAC way of naming, again, as I just mentioned, longest continuous carbon chain, not always the straightest. We do find our groups that are attached. We want to give a prefix if there's more than one in there. Now, speaking of those groups, as I mentioned before, they are oftentimes referred to as alkyl groups. They basically are missing 1 hydrogen from the alkane because that, again, gives them a place to attach. And we do put YL at the end of the name, so ethyl, propyl, butyl, pentyl group, as you can see here, methyl group, ethyl group. Again, having 1 less hydrogen, and that is where obviously the attachment occurs. Now, there are certain groups that have special historical names depending on the way they are attached, and we could actually classify carbons as what is referred to as primary, secondary, or tertiary carbons. And a primary carbon is pretty much what it sounds like. It is a carbon that is directly attached to 1 other carbon. A secondary carbon is a carbon that is directly attached to 2 other carbons. And a tertiary carbon is a carbon that is attached directly to 3 other carbons. So primary, secondary, tertiary. Personally, I count carbons. Some people count hydrogens, how many hydrogens are there. So, you know, primary would have 3, secondary 2, and 1 for a tertiary. So carbons, I think it's just an easier way of doing it. So depending on sort of where the group attaches, primary carbon, secondary, or tertiary carbon, you can have a special sort of name for the group. This is our basically normal sort of groups, methyl, ethyl, propyl, butyl type groups. But here's a table of some of those special ones. Let's come back. We saw our isopropyl group, which is basically our CH3, CH, CH3, where the attachment happens here. And this is basically our secondary carbon. So this guy right here is a secondary carbon as it's attached directly to 2. And that's different than a normal propyl group where the attachment would occur at the end here at this carbon, which is a primary carbon. So the kind of normal propyl group would attach at the primary carbon. Secondary attachment gives us that isopropyl group. Here's that isobutyl group that we saw before. This is sec-butyl. Sec for secondary carbon is where it basically attaches in. And that's this guy right here attached to 1 and 2 carbons. And this is T-butyl or tert-butyl for tertiary. And that is this carbon right here is attached to 1, 2, and 3 carbons. So the attachment happens there. So these are some historical sort of common names that's used a lot. Isopropyl, T-butyl, sec-butyl, isobutyl. Those are some common sort of group names that are still used very commonly here. These are the IUPAC version of those names, which mainly nobody ever uses. They will roll with these guys for sure. All right, so let's take a look at some here examples. I think we talked about all those there. Alphabet. One thing when we are naming these things, we do put our groups in alphabetical order in our name. regardless of the number or the prefix. So kind of like what we did with the complex ions, we go alphabetical regardless of number or prefix. So if we look at this guy here, longest continuous carbon chain would be straight across here. I think will get us 1, 2, 3, 4, 5, 6. We could also go straight across and up to give us 6. Again, it doesn't really matter which way you go. 6 carbons in a row is going to be hexane. We have a group that's over here, which is a methyl group. And we would add that to our name here, which would be methylhexane. The next thing that we want to do is number our chain to give that group the smallest number. You can probably just see it here. If you go left to right, 1, 2, 3, 4, 5, 6, as opposed to going the other way where that group ends up at carbon number 5. So we definitely would want to go in this direction. And this would be 2-methylhexane in this particular case. Any questions on that name there? You could also do this if you want to draw a line structure. It would look something like this. And 6. So that would be 1, 2, 3, 4, 5, 6. And our methyl would be at carbon number 2 coming up like that. So that would be the line structure there for this particular one. All right. Yeah. Yeah. Yeah, so if you wanted to draw like an ethyl group, it looks something like that. Whoops. Yeah. And then that would be your 1 and your 2 with the carbons there. And then obviously if you just need to go more, you just kind of keep going. And that's the exact way. That would then become a propyl group that I just drew there. All right, let's see here. Let's take a look. All right, why don't you give this one a try, see what you come up with here. Look, so I think if I count it right, 1, 2, 3, 4, 5, 6, 7, 8, I think is a winner, yeah. I think you can actually get 8 a couple different ways. You can go straight across, I think will give you 8. I think you can start up here and come down and also get 8. 1, 2, 3, 4, 5, 6, 7, 8. So you can come here and kind of go that way. We'll get you 8 as well. So might as well just take the straightest one there to help us out. So the 8 is going to be our main chain. We also got some groups then attached, which would be 1 there, 1 there, and 1 there going on in that particular case. Super zoom in case you missed it there. Now, since 8 is our main chain, that would be octane that's happening there for the main part of our name. That right there is a 2-carbon group. That's an alkyl group, which would then become an ethyl group based off of ethane. That is our 1-carbon group based off of methane, which is a methyl. And this is also a methyl here. That means we do have 2 methyl groups in this compound. So that's like a dimethyl situation happening. And we also have an ethyl situation. Any questions so far? So we want to do a little bit of numbering. So again, our 2 options here would be go left to right. So that is a 1, a 2, a 3, a 4, a 5, 6, 7, 8. Or we could go the other way. 1, 2, 3, 4, 5, 6, 7, and 8. All right, so going this way, we end up with a group at 2. We end up with a group at 5. And we end up with a group at 6. Going the opposite direction there, we end up with a group at 3, 4, and 7. The way we want to go is the smallest number, and once again, it is as simple as 2 is smaller than 3. So we are going to go in this direction to do that. So we are going to put this in alphabetical order regardless of number and prefix. So it actually is going to be the ethyl that's going to come first, E before M. And our ethyl is at carbon number 5. So this would be like a 5-ethyl. We then have a methyl at carbon number 2. We also have a second methyl at carbon number 6. And that would be a dimethyl and an octane at the end of that there. So 5-ethyl, 2, 6, dimethyl, octane. Any questions on that name there? So really naming, it's just all about location and telling people where you can find everything is pretty much it. It's always these two things. It's always the longest carbon to start with, and it's always numbering to give everybody the smallest number. So largest carbon, smallest number is sort of what you look for when you go to name things. Any questions on that there? That's good that they agree with me, so that's good. All right, why don't you try these three here, see what you come up with here. There's actually three. We'll separate it right there. Okay, let's take a look, see how you're doing. So top one, I think 6 is a winner no matter which way you go. Again, I think you get to 6 multiple ways, but we'll take the straight across for 6. Again, I think you could also start up here on top and come down and get to 6 as well. So 6 carbons in a row is going to be our main chain there. We then would have some groups attached. So we got right there a 1 carbon group and a 2 carbon group happening there. So starting with the base of the name, which is based off of those 6, that is hexane. This again is a methyl group. That is a 2 carbon ethyl group. And again, we want to give the location. So you could probably see going right to left will work here. 1, 2, 3, 4, 5, 6. That gives us our first group at 2 versus 3 if we went the other way. That means we will go alphabetical order. So we will go with 4 ethyl, 2 methyl, and I ran out of room, so I'll go underneath it, hexane. Any questions on that there? Taking a look at the guy on the bottom left there, we got, looks like pretty straightforward. 1, 2, 3, 4, 5, 6, 7 looks like a winner. That is the longest that you're going to get. So 7 carbons going to be heptane with this guy hanging out there as a group. So base of our name here would definitely be heptane with a methyl group there in green. And once again, going right to left will give that group the smaller number of 3 versus 5 heading in the opposite direction. So this would be 3-methyl heptane. Any questions on that there? Last guy there, longest continuous carbon chain is, I believe, 1, 2, 3, 4, 5, 6, 7, and 8 actually is the longest continuous carbon chain. Again, won't always be the straightest, and that's going to be a winner there for that. Our groups then would be over here an ethyl group, and over here a methyl group that's happening. So 8 carbons in a row is going to give us the base of the name, which is octane. We will have our ethyl group here, our methyl group there, and numbering left to right, 1, 2, 3, 4, 1, 2, 3, 4, I'll count, 5, 6, 7. I feel like I missed one right about there. 5, 6, 7, and 8. Looks better that way. So going that way, we have a group at 3 and 5. Going the opposite way, 1, 2, 3, 4, which is obviously too large already. So we'll go with 3 and 5 as a great way of doing that. That means this is going to be a 5 ethyl, 3 methyl. I'll try to stick it in there. Octane in that case. Any question on any of those names? So always longest continuous carbon chain, find your groups, number your chain to give the groups the smallest number. Again, when you're dealing with alkanes, alphabetical order regardless of number and prefix. Any questions on any of that there? All right, one last thing here, just finish out a little bit of organic. And that is if we wanted to actually draw an organic compound from the name, it's actually the easier of the two because it basically tells you what to do. Always when you are drawing, you always want to work backwards. So since we are starting with the condensed formula, we would start with this guy, which is butane. That means we simply just want to lay out 4 carbons, which is what butane has, nothing else. That takes care of that. Since we are drawing this, you could call this carbon over here carbon number 1. You could call the carbon on the right carbon number 1. It doesn't matter since you're drawing. I'm going to call the guy on the left carbon number 1, which means 2,3-dimethyl at carbon number 2. There should be a methyl group, which is a CH3, and then carbon number 3, which would be right next door, should be a methyl group as well, and that would take care of that part of the name. At this point, you have nothing left of the name. Everything else is just going to be hydrogens to get carbon to 4. So the guy at the right has 1 line coming in, needs 3 hydrogens. Guy here has 3 lines coming in, needs 1. Guy here has 3 lines coming in, needs 1. Guy here has 1 line coming in, needs 3, and this would be the condensed formula. If we wanted to do, if we wanted to do a little line structure, you would start the same way. Start with 4 carbons, which looks like that. Carbon number 2 would be a methyl group, which would be right there, and carbon number 3 would be a methyl group right about there. I missed the carbon there, but kind of right there. And you can draw the line structure kind of the same way. So if we were doing this one, which is heptane, heptane means 7 carbons. So we'll start back here. 1, 2, 3, 4, 5, 6, 7. I'm going to again call this carbon 1, which means at carbon number 2, I should have a methyl group. Carbon number 3, which should be right next door, I should have an ethyl group, which would be a 2-carbon group. At this point, once again, everything else will just be hydrogens to get to 4. Will look something like this. And once again, if you wanted to do a little line structure, you would start with your 7 to begin with. And again, go into carbon number 2, which would be right there, just a line which would indicate a methyl group. Carbon number 3, as was sort of asked before, a little curve there to give us 2 carbons there, which would be an ethyl group. And that would be it in terms of that. Any questions on that there? Last one here, pentane would be 5 carbons. And again, I'm going to start this as carbon number 1, which means right here would be a chloral group, which would be a Cl. And at carbon number 4 would be a methyl group. And again, we will fill in the appropriate number of hydrogens to get up to 4. And now we would have our structure there. And if we wanted line structure, we would start with our 5, 1, 2, 3, 4, 5. Again here, Cl. And at carbon number 4, a methyl, just like that. Any questions on drawing, which I think, again, is probably the easier of the two, actually. Yeah. But always work backwards when you're drawing. Much easier. Start with sort of the skeleton and kind of fill everything in. And then everything else is just going to be hydrogens. Any questions on any of that? All right, I think that's a great place to stop.